Usually when I record videos for my classes, I'll have little snippets of text with an example or definitions or things like that. Um, this is the first time I've ever actually tried to lecture an upper level class with a video. So we will see how this goes. So as you know, this is section 3.4, proof by cases. We've actually done a little bit with proof by cases already, looking at some, and if you look back through your notes, you'll see where we divided the proof up into, well, this is going to happen or this is going to happen, therefore, this is how the proof is going to work. Now we're going to formalize that and see how it works. So I want you to consider, first of all, this proposition. If n is an integer, then n squared plus n is even. Now, we've seen propositions and statements similar to this in the past, but what would usually happen is we would specify that n is even or n is odd. This proposition doesn't do that. We just take any integer we want, and then we want to conclude something about this expression right here. We want to say something about its parity. A number's parity is whether it's even or it's odd. So we want to say that if n is an integer, then n squared plus n has even parity, or it's even. Don't worry about the parity term. You'll talk about that later, maybe in abstract algebra. In any case, what we do here, we do a proof by cases. That is, we're going to exhaust all possibilities by listing them out. And that's actually a super important point that I'm going to refer back to over and over and over. We want to exhaust all possibilities when doing proofs by cases. You have to exhaust all the possibilities by listing them out and then proving the proposition holds in every case. Now, in this case, it's pretty simple. In this case, that is an intended pun. The two cases are simple. Either n is even or n is odd. And so what I would like you to do is pause the video and verify to yourself that n squared plus n is always going to be even. Whether you start out in even or you start out in odd, you'll always get that n squared plus n is going to be an even number. So pause the video right now, prove that to yourself, and then come back and start the video back. And 3, 2, 1. Welcome back. I hope you had a good time proving that and that you got coffee or tea or whatever your caffeinated beverage of choice is. All right, moving on. Here's why proof by cases work. It's a little more complicated than this because I can have more than two possibilities, but generally speaking, the logic behind how proof by cases work depends upon this. The expression, what P, Q, and R are going to be propositions or statements, and the compound statement P or Q implies R. That's logically equivalent to saying P implies R and Q implies R. And you can draw a truth table to verify that. If you want to pause the video right now, do the truth table. It's a nice little exercise and a nice little refresher. I'm not going to do it. Moving on. Here are some situations to keep in mind when you're going to do proof by cases. Now, these are not all of them. Obviously, it's just to kind of give you an idea. So, first up situation is if n is an integer, some cases you might consider would be case 1, n is even, case 2, n is odd. That's one possibility. Suppose you have the hypothesis that says m and n are both integers, two different integers. Now, this is a situation where you may have, where there are more than two cases. The first case is m and n are both even. Second case, m is even, n is odd. Third case, m is odd, n is even. Fourth case, both of them are odd. Now, the important thing to keep in mind is we have exhausted all of the possibilities with these four cases. We exhausted all the possibilities of how m and n could be odd or even together. Another situation, x is a real number. We could have case 1, x is rational, case 2, x is irrational. However, the same hypothesis, x is a real number, we might want to look at cases where x is 0, x is not 0. Or, if x is a real number, we might want to consider x is greater than 0, x is equal to 0, x is less than 0. Notice I'm starting with the same hypothesis in all of these, but there's all these different possibilities, and these are not all of them. And just later on at the end of these notes, we're going to see a situation where we're going to combine these two together for a couple propositions. We'll combine those two together into one case, where case 1 will be x is greater than or equal to 0, and case 2 will be x is less than 0. Okay. Sorry that my cursor kind of seems to jump as I move it. I think I must have some dirty places on my iPad. So I think after I finish this page, I'm going to pause the video and clean it up. Okay. Anyway, next possibility, A and B are real numbers. Case 1 would be A is equal to B. And look, the first typo of the day. How wonderful is that? So what that should actually say is, zoom in, it should say case 2, A is not equal to B. That is, of course, what it should say. All right. So anyway, A and B are real numbers. I could have case 1, they're equal to each other. Case 2, they are not equal to each other. I want to make that A a little bit better looking. I think I just made it worse. Damn it. This is what I get for trying to I guess I could go back and cut all this out, but I'm not going to. This is going to be one take. Okay, I'm going to make that A look better. There we go. That's good enough for me. All right, moving on. All right, A and B are real numbers, and then I could have case 1, A is greater than B, case 2, A is equal to B, case 3, A is less than B. So anyway, the point of all of this is you can have different situations. That is, you could have different cases for the same hypothesis, okay? And as I say right here, the case you use will depend on the proposition you'll ask to prove. That is, if your hypothesis is just x is a real number, you'll use this one or this one or this one. It just depends on what you're asked to prove, and you need to be a little bit flexible with that. Okay. Next, we're going to prove this proposition right here. For each integer n squared minus 5n plus 7 is an odd integer. Now, this looks like the one we started with initially. We're starting with an integer n, and we want to prove that this expression is odd, which is a very good indication that we are in this type of situation, where we're going to assume n is even and then n is odd and see if we can prove the proposition. And that's what we're going to do on the next slide. So we are now looking at this proposition. For each integer n squared minus 5n plus 7 is an odd integer. So here's how you set up proofs for, and I'm sorry if there was an audio hiccup right there. I had paused it to make sure my Bluetooth mic was still working. My Bluetooth headphones were still recording audio. And I think when I unpaused it, I started talking before I was ready. I promise you, I'm going to get all the kinks worked out. Okay, so what we're doing. So here's the proposition. For each integer n squared minus 5n plus 7 is an odd integer. All right. So here's how you, okay, like I always stress in class, when you do a proof, you want to tell them what you're going to tell them, and then tell them what you've told them. So if you're doing a direct proof, you'll say, we will prove this by assuming P and showing Q. If you're going to prove by contradiction, you'll say, we will prove this by assuming P and towards a contradiction, assume not Q, and then proceed with your proof. Well, you do something similar for proofs by cases. So here's what we're going to say. We assume that n is an integer and show that n squared minus n plus 7 is an odd integer by examining the case where n is even and the case where n is odd. So basically, you write down what the hypothesis is from the statement of the problem, and then explain what you are going to prove and talk about what the two different cases are. And so that's how you let the person who's reading the proof know that it's going to be a proof by cases. Now, at least initially, we are always going to write out case 1 and case 2. Now, we're going to start case 2. Now, we're going to stop doing that after a while, but for now, we're always going to write out what those cases are very, very explicitly so that we can see exactly what we're talking about. And I also want you to do that. Okay, I also want you to write out those cases explicitly. So, here we go. Let's do this proof. All right, so we assume that n is an integer and show that n squared minus 5n plus 7 is an odd integer by examining the case where n is even and the case where n is odd. Case 1, assume that n is an integer that is even. So what does that mean? In this case, there is an m, an integer, such that n is equal to 2m. Therefore, so what would be a good idea now is to pause the video and write this proof. Okay, I'm also going to write it in just a second, but it would be very good practice for you all to go ahead and pause the video right now, work out the rest of this case, and then see what I do and see if we did the same thing. I got a pretty good suspicion that we will do the same thing. Go ahead and try that, and I'll wait 2 or 3 seconds before I go ahead and do the proof. All right, so since we've assumed that n is even, n can be written as 2 times m. Therefore, the expression n squared minus 5n plus 7 is equal to, I'm just going to substitute 2n, m squared plus 5 times 2m plus 7. And then, you know, we're just going to multiply it out. So this is equal to 4m squared. Oh, just notice there's a typo up there. That should be negative. So the problem is going to be equal to 4m squared minus 10m plus 7. So keep in mind what we're trying to do. We're trying to get that n squared minus 5n plus 7, that's negative. Excuse me, that's an odd integer. So I want to end up with plus 1 at the end. So this is equal to 4m squared minus 10m plus, I want to end up with a plus 1 at the end. So I'm going to write that like that. 6 plus 1. But now I can factor out a 2 everywhere. And this is 2 times 2m squared minus 5n plus 3 plus 1. But this can be written as 2, say, times k plus 1 for k equal to, k is going to be 2m squared minus 5m plus 3. So what does that give us? That gives us that, well, first of all, we note that k is an integer by our old buddy closure. But then we're done. Therefore, n squared minus 5n plus 7 which is equal to 2k plus 1, is odd. Now, that's just the first case, okay? So there's the whole thing on the screen at once. So you can take a look at it. So there's the whole case. This looks very, very familiar. We've been doing stuff like this for a very, very long time. The only difference is this isn't all of the proof, right? We still have case 2 down there. So let's take a look at that. Again, it would be very, very useful for you to go ahead and pause the video and do the proof yourself. Now, by the way, because I know some of you are very particular about your boxes to end the proof, I couldn't make LaTeX slide that end of proof box down. I couldn't put any space in there. I mean, I could have. I just didn't want to take the time to look up to fight with it or look up how to do it. So that's why that's there. My apologies if it gets on your nerves. Just mark it out or something if it does. All right. So now we're going to assume that NZ is odd. In this case, there is an L, an integer, such that n is equal to 2L plus 1. Therefore, well, we're going to play the same exact game. Therefore, n squared minus 5n plus 7 is equal to 2L plus 1 squared minus 5 times 2L plus 1 plus 1. Oops, that's ugly. Plus 1 plus 7. Multiply it out, and you'll get something that looks like 4L squared plus 4L plus 1 minus 10L plus 5 plus 7. Well, look, there's already a 1 that I want to end up with, so I'm just going to combine like terms, but move that 1 to the very end, and we end up with this. 4L squared plus, how many L? I think is going to be minus 6L. That's an L. And then this is going to be plus, what's 5 and 7? 12 plus 1. And remember, I wanted that 1 at the end because I want to show that this whole expression is odd. All right. But this works out the same exact way. I'm able to pull a 2 out of all these terms. So it's 2 times the quantity of 2L squared minus 6L plus 6. That's a mistake right there in the middle. That is not 6. That is a 3 plus 1. So that is equal to 2, we'll say J plus 1, where J is equal to 2L squared minus 3L plus 6. That is, so we'll say, since J is an integer by closure, we're going to get that n squared minus 5n plus 7 is odd. So we've done both of the cases. Okay, we've done both of the cases. There is case 1 when n is even. Here is case 2 when n is odd. And then we're going to sum it up. Okay, we're going to say at the very end, in both cases, n squared minus 5n plus 7 is odd. And that, my friends, is the end of the proof. All right, moving on to the next page / next slide. Consider this proposition. For all real numbers a and b, if a times b is 0, then a is 0 or b is 0. Now, when you want to prove something like this, that is when you want to, when you're assuming that a times b equals 0 and you want to show that one or the other is 0, The temptation here is you want to divide both sides by A and conclude that B is 0, or to divide both sides by B and conclude that A is 0. But you can only do that if you know that something is non-zero. So one approach to this is the following. Just take your two cases to be A is 0 and A is not 0. And we'll see that if A is 0, one part of this OR statement holds. If A is equal to 0, another part of this OR statement holds. So what that means is, in either case, and this exhausts all the possibilities, in either case, this OR statement holds. Because remember, for an OR to be true, you just need one of them or both to be true. So let's see how we could do this type of proof. So what we're going to do is we will assume A and B are real numbers and that their product is equal to 0. That is, I'm assuming all of the hypotheses of the problem. And we will show A is 0 or that B is 0 by two cases. Well, by considering two cases. Case 1, suppose A is equal to 0. Okay, we're done. All right, we're done. Because if A is equal to 0, that means that A is equal to 0 or B is equal to 0. So that's all we need. If A is equal to 0, then we're actually done. We're done. So now look at case 2. This is the only interesting one. Case 2, suppose A is not equal to 0. And remember, we are doing this because we want to exhaust all the possibilities. A common mistake I see people make is they'll say, for case 2, now suppose B is equal to 0. But that doesn't exhaust the possibilities, okay? Either A is 0 or A is not 0, full stop. That is all that can happen. So if A is not 0, then A times B equals 0. Divide both sides by A, which I can do because A is not 0. Then that gives that B is equal to 0. But then we're done, because if B is equal to 0, then A is equal to 0 or B is equal to 0. And that's actually the end of the proof. Now you can write a little extra sentence in there that says, in both cases, A is equal to 0 or B is equal to 0, and then draw your box. But this is it. This is all that we have to do. Let's talk about absolute value. Now, you have probably seen the definition of absolute value in calculus because you've had to, or maybe physics, if not calculus, if you had any physics, because in order to take the derivative of a piecewise defined function, you have to divide it up into pieces and then take the left derivative and the right derivative and see if they match up. And as we know, the absolute value doesn't have a derivative at 0 because the left and right derivatives don't match up. So maybe you've seen this definition before. But if not, then yay, I get to introduce you to it. Now, our intuition about absolute value is that the absolute value of a real number is that it's the distance the number is from 0, which is absolutely true from kind of a geometry point of view. If you think of numbers as existing on the real number line, the absolute value of a real number is how far it is from 0. But it's not super useful for calculus and for analysis. To prove anything about absolute value or to generalize it for other number systems. Like there's an idea of an absolute value of a complex number or an idea of norms in general. To generalize it, we need a more formal definition. And this is what that definition is. So for x, a real number, that should be our fancy math R. That should be fancy math R right there. Okay. So for R, a real number, we define the absolute value of x, for x, a real number, we define the absolute value of x by the piecewise function. Absolute value of x is x if x is greater than or equal to 0, and the absolute value of x is negative x if x is less than or equal to 0. Now, if this is your first time seeing this, it's going to look a little weird because, you're going to be thinking, wait, the absolute value is always a positive number. So why is that negative sitting there? Let's look at some examples, okay? So let's just note a couple of things. Using this definition, the absolute value of 2 is going to be, okay, well, 2 is greater than 0. 2 is greater than 0, which tells us that the absolute value of 2 is going to be the number itself. Okay, absolute value of 0. Well, 0 is greater than or equal to 0. So absolute 0 is going to be the number itself. What about absolute negative 2? Well, in this case, we are down here, okay? Because negative 2 is less than 0. So that means the absolute value is going to be negative what is written down. So the absolute value of negative 2 is negative 2, which turns out to be that positive number. Okay? The reason we have that negative in the definition is because we do want it to always be positive. And how do you turn a negative number positive? You multiply it by negative. So that's how the definition of absolute value works. Moving on to the next page slash slide. Look at this theorem that involves absolute value because we just looked at it. So what we're going to do here is we're going to let A be a positive real number. This is important. A is positive. A is a positive real number. And for each real number x, we have two different parts of this theorem. Number one says the absolute value of x is equal to A if and only if x is equal to A or x is not equal to A. A lot of stuff going on in this one, in this statement. We're going to come back to it. The second part of the theorem says absolute negative x is equal to absolute x. Now, proving part 2 is actually a homework problem, so you'll be able to do that one. That's a homework problem. We're going to focus our attention on this number 1 right here. Okay, so think about everything that is going on. I'm going to move this up so I have lots of room. Think about everything that is going on right here. First of all, I have a biconditional statement. It's an if and only if, so I have to prove both directions of that. And not only do I have a biconditional, but I have this disjunction right here. I have this or statement inside that biconditional, one part of that biconditional. So we'll have to keep that in mind when we're doing the proof. Let's just jump right in and go ahead and see if we can prove this. So what we're going to do first is, well, I guess we'll just prove, we'll say proof of part 1, because we're only proving the first part of that theorem. So it's biconditional, so we'll do the forward direction first. So we suppose that absolute x is equal to A, and we will show that, what do we want to show? Show that x is equal to A or x is equal to negative A. Remember, to show an or statement is true, you just got to show one or the other is true. And the way we're going to do this is we're going to consider the cases, first of all, that x is greater than or equal to 0, and the second case is that x is less than 0. Sorry. Now, why are we looking at that? Why are those the two cases that we use? We already know something about A. A is a positive number. And since x is our variable, so to speak, in the hypothesis here, the hypothesis in this is something about the absolute value of x. We know the absolute value function changes definition at 0. So that's where these two cases come from. And it's common for these to be the two cases when you are proving something about absolute value. Okay, so let's move on with this. Let us proceed. So case 1, we assume that x is greater than or equal to 0. Okay, since x is greater than or equal to 0, that tells us that absolute value of x is equal to x. Right? The absolute value of a number that is greater than or equal to 0 is equal to x. But what was the hypothesis of the forward direction of that proof? It was that absolute value of x is equal to a. Well, since absolute value of x is equal to x and absolute value of x is equal to a, that tells us that x is equal to a. But that is exactly part of that or statement that we wanted. So we're done with that case. In the case that x is greater than or equal to 0, then we've proven that statement. So now let's look at the second case. So case 2, now we'll assume that x is less than 0. Well, that means that the absolute value of x is equal to negative x. But remember, the initial assumption was absolute x is equal to a. So that tells us that negative x has to be equal to a. Right? Because that assumption said that these two are equal to each other. That absolute value of x was equal to a. But since x is less than 0, absolute value of x is equal to negative x. And so, what I'm using is what's called the transitive property of equality, which we'll get into when we do equivalence relations. But that we're going to end up with negative x is equal to a. But that was also part of the or statement. And so we're done. At least we're done with the forward direction of the proof. Let me change back to blue. So in both cases, if absolute value of x is equal to a, then x is equal to a, or x is equal to negative a. And so that is the end of the forward direction. So I'm going to leave that up for just a second, and you can pause the video now if you want to write that down or finish, check what you'd written down. I'll wait about 3 seconds, and then we'll do the backwards direction. And boom, screen's blank. Now we're going to go ahead and prove that backwards direction. So let me zoom in here a little bit. So we're going to prove the backwards direction. That is, we assume that, a little bit more room. We assume that x is equal to a, or x is equal to negative a, and show that the absolute value of x is equal to a. All right. So the two cases are given to us. This is that classic example that I talked about, where the way that proof by cases work depends on that logical equivalence. So our two cases are exactly what we have stated here. x is equal to a or x is equal to negative a. So let's just write them down. Case 1, we assume that x is equal to a. Okay. So what does that mean? If x is equal to a, that means the absolute value of x is going to be the absolute value of a because they're equal. But the absolute value of a is equal to a because a is positive. That was one of the initial things we assumed about a. And so we're done with this case. If we assume that x is equal to a, then we get that absolute value of x is equal to the absolute value of a. All right, so what about the next case? What about case 2? Case 2, assume that x is equal to negative a. Okay, well, same thing is going to happen, or rather a similar thing is going to happen, but we're going to start looking at the same way. Absolute value of x is going to be absolute value of negative a, but this is going to be negative a by the definition of absolute value, because negative a is less than 0. Okay, negative a is less than 0. But what do we have here? This is going to give us that absolute value of x is equal to negative a, but that's just a, which is exactly what we wanted to prove. In either case, or rather in both cases, absolute value of x is equal to a. And so we, well, I've already erased it, so I can't show you the forward direction of the proof, but we proved the forward direction. We just proved the backwards direction. And so we're done. And so if you like, we can sum this up by saying, therefore, absolute x is equal to a if and only if x is a or x is negative a. And there's the end of the proof. We are in the home stretch now. Last theorem that I wanted to cover. Now, this is really useful when you take analysis, when you take your real analysis course, or complex analysis even. But you'll use this last one all the time. Literally, you'll use it constantly in real analysis and real analysis 2. It's one of the most commonly used ones. Let's look at the statement of the theorem first, though. A is going to be a positive real number again. And for all real numbers x and y, number 1, absolute x is less than a if and only if negative a is less than x is less than a. Now, this is the one that we're going to prove. This is also the only one that involves a. What you're going to prove in your homework is that the absolute value of x times y is the absolute value of x times the absolute value of y. In other words, the absolute value of the product is the product of the absolute values. Really useful to remember when real analysis. Number 3, the triangle inequality. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. In other words, if you add two numbers together and take their absolute value, you're always going to have something smaller than if you add up their absolute values separately. And again, that is called the triangle inequality. Exercise, figure out why it's called that. Okay, draw some triangles, figure out why it's called that. Like I said, we're going to prove 1, 2, and 3 are going to be some of your homework problems. So again, since we have a biconditional, we're going to prove both directions. So proof of 1, we suppose that absolute x is less than a, and we're going to show that negative a is less than x is less than a. And we will do this by cases. Case 1, is, well, the only thing we have to work with is what x is. So it's going to be the same thing. Case 1 is we're going to assume that x is greater than or equal to 0. Well, if that's true, then that means absolute x is equal to x. Okay. However, we've assumed that, well, let's see. Let me just say it like this. Let's say that this is going to be less than a. I'll write that as one string of equations and inequalities. Absolute value of x is equal to x because x is greater than or equal to 0. But absolute value of x is assumed to be less than a. Okay, it's assumed to be less than a. So we get that x is less than a that way. Right? So next, I want you to note that since a is positive, negative a is less than 0. Okay? Thus, negative a is less than x. That's true because we assume that x is greater than or equal to 0. But we already know that x is less than a, and this is the result we wanted, that negative a is less than x is less than a. So case 2, we're going to assume x is less than 0. Well, what does it mean for us if x is less than 0? Then absolute value of x is going to be equal to negative x, which is less than a, right? Why? Well, absolute value of x is negative x because x is less than 0, and that's how absolute value is defined. And remember, we're still proving this forward direction, so we have this supposition that absolute x is less than a. So absolute x, which is equal to negative x, is less than a. All right? So what does this give us? This is going to allow us to say the following. But x is going to be less than a because x is negative and a is positive. So what do we get from that? Well, we get that we have x is less than a and negative x is less than a. But this is going to give us that a is negative a is less than x, and this is going to give us that x is less than a. Forgive me for getting messy with my symbols and not writing this super formally. It's really annoying to do this on an iPad. So just excuse my abuse of notation and my sloppiness of this proof. But the point, I think, still works. We still have everything we wanted. Okay? Here is initially what we wanted to prove, the forward direction of this. That is, if absolute x is less than a, then negative a is less than x is less than a. And that's exactly what we've done here. So for the forward direction, we assumed absolute x is less than a, have two cases. In case 1, we ended up with that expression, and in case 2, we ended up with that expression. So I'm not going to write this out, but we know that now in both cases, we got what we wanted. That's still only the forward direction. So let me pause the video, erase all this, and then we'll do the negative direction. All right, I said pause the video, I meant pause the recording, which is what I did. So now we're going to prove the backwards direction. That is, we're going to assume, that negative a is less than x is less than a, and show that absolute value of x is less than a. All right. So in this case, or in this situation, the cases we're going to look at are just going to be what you would normally use for the absolute value of x. So case 1, we assume x is greater than or equal to 0. What does this tell us? This tells us that the absolute value of x is going to be equal to x, okay? But that's less than a. That's less than a because of our hypothesis. This part of this compound inequality in our hypothesis was that x is less than a. So what do we get from that? We get that absolute x is less than a, which is exactly what we wanted. So absolute value of x is strictly less than a. Let me write that again. Strictly less than a. Okay. So, well, that is all for case 1. We proved what we wanted. So case 2, we assume that x is less than 0. Well, that gives us that absolute value of x is going to be equal to negative x. Okay. So what can we do from here? Okay, use the hypothesis. Remember what I say a lot, or what I used to say a lot in class. I'm not going to say it anymore, unfortunately, unless you guys have me for, I don't know, topology or complex or something. If you're stuck on what to do in a proof, see what you haven't used yet. Okay, we haven't used this. We haven't used this assumption yet. So think about how we can use this assumption along with this right here. And I'm going to pause for a second and say that it's very unfortunate. Again, it's very unfortunate. This is how the semester is turning out, because I can't see your faces and I can't see where you're confused. And all I'm doing is I'm just writing it a proof. So please take advantage of those office hours that I'm going to be doing every day. Excuse me, every Tuesday and Thursday. And please email me. If you want to meet some other time. If you get stuck following a proof, write down the timestamp so we can look at it together and we can figure out what's going on. But this, I think, is a place where someone may get stuck. Okay, so they have the second case, assuming x is less than 0. Well, that means absolute x is equal to negative x. Where do you go from here? Okay, the only thing we haven't used yet is this hypothesis. So how can we relate this with this? Well, here's how we can do that. So I'll say it like this. Actually, let me make my screen a little bit different. I'll say it like this. But negative a is less than x is less than a. So that means that a is greater than negative x is greater than negative a. So how is that useful? Look at this piece. Okay. In other words, negative x is less than a. But the absolute value of x is equal to negative x. So how do we conclude it? So that means the absolute value of x is strictly less than A, which is what we wanted to prove. Okay, that is exactly what we wanted to prove. Okay, look at here, backwards direction up here. If this is true, then absolute x is less than A. Well, that's what we did here, and we did it by cases. Okay, we did it by cases. So yeah, that is the end of the proof. Big happy box because we're done. Actually, I want to. Let's not do that. Let's do this. Great big happy box with a smiley face because we're done with the proof. And he looks a little bit sardonic, which is appropriate, I guess. Yeah, so there we go. All right, guys, that is the end of proof by cases. I don't know how long this is going to be. I'm probably going to break this up into several videos. Of course, I'm saying this at the very end, so you already will know whether I broke it up into several videos or not. At any rate, let me know if you have any questions. Start working on the homework, and hopefully I will see you virtually very, very soon. Bye-bye.